So we're talking about lesson 3 today. It's called Diffraction and Interference of Water Waves. So before we move on further, we just wanted to do a couple of review of what waves are. And in particularly, we're going to be talking about this thing called the transverse wave. What a transverse wave are like waves that you see in like water and stuff. So basically, if there's no disturbance in the water stays calm. And if there's somebody over here at the starting point, they are, say if there's like a drop of water comes out and then it starts dripping, what happened is it's going to start to create a wave that looks like this. Okay, it goes up and down like that. Okay, and you need to understand that we are going to be doing a certain labeling. The highest point of the peak, we call it the crest. So that is when it's highest from the zero equilibrium, when there's no disturbing, we call it zero. That's the highest point. The lowest point are called the trough. Okay, and we have this thing called the wavelength. Wavelength has a symbol of lambda. Okay, lambda. I think I spelled length wrong. I'm just gonna fix that. Okay, lambda. So it's read as lambda. It's a Greek alphabet and it's measured in meters. Wavelength is like what it said, the length of one wave. So if I were to pick a point, I'm gonna make a small. If I am to pick a starting point here, do you see how the wave goes up and down and up? From the repeating point, the distance between them, if I were to measure this blue thing is one wavelength. And wavelength can be measured from the 0 point to the 0 point. We call the 0 point the node, okay? But actually, we're going to talk about that later on, okay? It can also be measured from another point. Like say if I wanted to start right here, okay? If that's the starting point. So I'm at a crest, goes down to the trough, to the crest again. See how when the wave repeats, that's also called one wavelength. And it's the same thing as the blue one that we have, right? So you can measure it any place, but wavelength is where it's repeat again. The wave repeats again. So I'm going to do the third one. If I say want to start at this trough down here, troughs goes up and goes down again, that's one wavelength. Okay, so one wavelength is when the wave repeats itself again, the length for one wave, that's one wavelength. Okay, there's another review called the universal wave equation, which you also will need to know. Okay, V equals F lambda. V stands for the speed of the wave. So how fast the speed is moving. So that's the speed is measured in meters per second. F is for frequency. Okay, frequency is in 1 second. How many times is the wave being produced is measured in hertz. The base unit for hertz is basically the inverse of a second. So in 1 second, how many times? And then finally, we already talked about what the wavelength is. Wavelength is measured in meters. Okay, so that's another big equation that you will need to know and you will need. Okay, so we've now labeled a crest and a trough. Okay, it's hard to draw the picture. So what happened is we actually, can you imagine if this is your eye and you are looking from above the water wave. So your eyes is up here. This is your eye and you're looking at it. And what happened is the wave, we use this thing called the wave front. Okay, if I'm actually doing the bird eye view of the wave and the wave are safe being generated, what happened is we always draw just the crest. We call the crest, we would draw the wave front. Okay, so if I were to draw this water wave and I'm looking at it from above, you know how water, the dripple, it has like a ripple effect with a circle and it starts going outwards. We would only draw the crest, and if this is the starting point of the wave, you would only draw the crest, and this is one wavelength, and that's another wavelength. So it's crest to crest. Okay. So here's a picture. if we are focusing on one of the one on the right hand side of his hand, and he's making a ripple that's happening, like if we're only focusing on this one, okay? And do you see how there's like the crest and the trough, and the crest and the trough, and the crest of the trough as they go out? So in order to express it easily on a piece of paper, we would only draw a certain thing, and then we're going to talk about how we want to do that. So the wording that we're going to use is I'm going to make this thicker. Let's try blue. Okay, we're going to call this point the source. Okay, S1 of the source. And every time when we see a crest, we're going to do a solid circle. Okay, so anything in here, see this oval? I can't draw all of them. These are the crest, and we only draw the crest part that is the highest point on the wave. Okay, we use a solid line to represent it. And then anything that is the low point, the trough, we would use a dotted line to represent it. Then that way we can study the wave a bit better. So in between any two blue line, that's one wavelength, but in between any green line is also one wavelength, okay? So now going back to the lesson, we're going to take a look at this humongous picture here, okay? Because basically what this lesson is called the interference of water wave. We would have 2 point source, okay, S1 and S2, and each of them generating crest and trough circles, and they're going to start interfering with each other. So you'll be like, what is interference, okay? So this is already an image to show you interference, but I'm going to start to draw a picture. Okay, if I have one wave, okay, and I'm going to make this into blue. Okay, if I have one wave, and then I tell you I have another wave that is exactly the same, but I'm just going to trace it with a different color. Okay, I'm just going to go exactly the same waves, and they have different color. Okay, what happened to them is basically as the wave starts interfering with each other, something neat is going to happen. Okay, if I have situation like this, when they're actually lining up with each other, when I have a crest meeting a crest, what happened is, if this is the zero line, what happened is the two crests that are meeting will actually become a giant wave at the top. If I have two trough that is meeting, it's going to make a super trough. So it becomes magnified, and they become really, really big. In cases like this, we call this the constructive interference, because they're building on top of each other. Okay, we call this the constructive interference. They become bigger wave. But what you would notice is that you would still have these points that you would have nothing happening. The 0 point, we call them the node. Okay, the nodes are the zeros. Okay, all right. What happened to this wave as they keep traveling to the side? Like say if I have traveled this a little bit more, I don't want this guy. Okay, say something like that. What happened is the whole wave, every single wave actually start canceling each other. My overall wave, it's actually a complete zero. Okay, we call this a destructive interference. They are destroying each other, so I am now not making a wave. This is when, if we're in class, we would be playing slinkies. We'll be playing hanging stuff above the hallway, and we will be playing slinky. All right, so let's highlight this again. Okay, what is interference? Constructive interference is when the wave build each other up, producing a resultant wave of greater amplitude at the given wave. So this is a constructive interference. I got wave 1 and wave 2. They build on top of each other, and they get an overall big wave. Okay, what is the destructive interference? Okay, destructive interference happen when the wave diminish one another, producing a resultant wave of lower amplitude than the given wave. This is an example of a destructive interference. Notice the wave are shifted and off, and they start canceling each other, so you have a zero wave. All right, so now let's really get into the lesson now. Okay, so this is the key thing with the lesson. Okay, we have this thing called the two-dimension interference. Okay, so let's go one at a time. Okay, so I'm going to start from fresh. Okay, 2-point source. So what is a two-dimensional interference? 2-point source vibrating at identical frequency and amplitude. They have to be the same. And they actually produce these things called an interference pattern. And that's a pattern that we are going to study. Okay, and remember, we talked about that already. A note is when the wave produces zero displacement. The overall is right in the middle. Okay, and the nodal line is actually the line or curve that you have an entire line of destructive interference. All right, ready? So let's study. I'm not going to start with this picture. We're going to draw the picture out. We're going to work on it together. Okay, so I am talking about source 1. Okay, source 1 is going to be making circle wave. Okay, and I'm going to start to draw the crest. Crests are the standing up tall one. And then I'm going to draw a trough. I'm going to draw a crest. And I'm going to draw a trough. That's one wave. So similar to the picture that we were talking about. I don't know if I saved it, which I didn't. Okay, similar to the picture that we were talking about. So just one object. At the same time, I am going to introduce a source 2. Okay, source 2 goes like this. So I have another object, another identical object, and I'm going to say this is source 2. Okay, I'm going to say at the same time right there, I'm going to be generate the wave up and down with that green object. So I'm going to have a crest, and I'm going to have a trough. I'm going to have a crest, and I'm going to have a trough. See, I'm creating this interference pattern. Okay, so let's take a look at, I'm just going to draw a couple more. Crest and trough. The key thing is it has to be identical frequency and identical wavelength, right? Or it's not going to be a consistent pattern that we can study. You don't have to draw this down. It's already all in your picture, so I just wanted to make sure that I draw it out so you can see where my explaining came from. All right, so we talked about constructive and destructive interference, right? I'm going to use a pink dot. A pink dot are the ones that are having destructive interference. Okay, or in another word, those are the nodes. And a destructive happens if I have a solid line intersecting with a dotted line, right? A crest and a trough, when they meet, they cancel. Okay, so let's take a look at this thing. Okay, so say right here, there's a green dot, there's a pink dot, because I have a intersection of a solid line and a dotted line. Right there. Right there. I'm just picking out spot that is a dotted line intersecting with a solid line. All right, so you would see, and then where the pattern came from is if you now take a look at this nice picture that they have. All right, let's take a look at the prefix. Okay, so first of all, you need to know the crest and the trough, right? The crests are solid line, the troughs are dotted line. Okay, the next thing you need to pay attention are the sources, S1 and S2, because later on you're going to need to know information like what is the distance between the sources and things like that, right? Then the middle line is also something that I want to look at. The middle line is right here, right? That's the middle line, because like you see how like the straight line that goes all the way to the bottom, that's the middle lines. Okay, and then I need you to take a look at the two circles. There is a circle with a solid dot. So I'm going to highlight this for you. This dot, a solid, is when I have constructive interference. And then if I have an open dot, those are the no. Okay, so that is the purple dot that I was coloring in, right? Okay, so that was when I was doing the purple dot with the note. Okay, all right, so let's just take a look at, basically you only care about the notes. Okay, see these open dots, these are the notes, and see how they all lined up in here. And do you see how this line is closest to the middle line? We called it n equals to 1, nodal line number 1. Okay, if I shift towards the right hand side and I go to the next nodal line, remember how we said at the intersection of a crest and a trough, those are the node, the 0, this is n equals to 2, and so on and so forth, and this is n equals to 3. On the same time, on the left hand side, I also have the open dots. This is n equals to 1, this is n equals to 2, and this is n equals to 3. Okay, all right, so I have a video to watch to show you just to make sure you're getting it. All right, I don't know if you can hear it, but I can post a video. The key thing is I need you to see how the wave goes, okay?
A little pond where we can see this with water waves. Sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wave fronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern.
Do you see the interference pattern?
This pattern is created by the ripples from the two sources interacting with each other.
Okay, if I take a look at this screenshot that I took of him making the ripples, the nodal line, okay, the center line, first talk about the center line. The center line is right here in the middle. This is the center line that I was talking about, right? This is the middle. Okay, do you see the first dark line? I don't know if I can make it into a purple. The nodal line 1 is right here. This is where all the zeros are. This is n equals to 1. At the same time on this side, we have n equals to 1. Okay, and then the next nodal line is right here. Those are the wave when they are canceling each other, and your nodal line number 2 is over here. Okay, now we're going to go back to the video.
Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there. And this is exactly what was happening with the light.
Okay, so now that we understand the lab, how it goes. So imagine scientists would set up this lab setup that you can have 2-point sources that are continuously making waves. And by studying the pattern, they can then work out many different things that could be useful in the future. Okay, especially when we get to lesson 5, we will talk about that in detail. Okay, so definition at this point. Okay, there are symbols that they would use. First of all, are we okay that we use n for the nodal line, right? So we said that this is n, n1 and n2 being from the center moving outwards, n1 and n2, okay? And we have n1 and n2 on either side, right? And in this particular case, depending on the wavelength, depending on the distance, they only produce 4 nodal lines, okay? Other things that you might need to know is the distance between the 2-point source. We call it distance d, okay? And then we have this line that is called the right bisector. And let me see if I can see. This line right here in the middle, this is the name that's called the right bisector. Okay, and it's 90 degrees to that line. And other things that you do have are wavelength, right? So if I take a look at any point here from one crest to another, that's a wavelength, right? So you can physically measure it. So there are all these different symbols that I could have, okay? All right, so let's go on to what is the pattern that they found. Oh, I forgot to highlight. Just highlight these couple of things, okay? So this is called the two-point source interference. There's two sources that are generating the wave. We can directly measure the wavelength, and we call it S1 and S2 for being source 1 and source 2. And then we have this thing called the right bisector, okay? All right, so this is what they noticed. So what they found is if you pick any point along N1, so they picked this point, they call it P1, and they found that if they take P1 and they take a ruler and they join it to S1, if they draw this line, and that is P1S1. So this line right here is P1S1. So the distance between point 1 to S1. The reason why we use 1 is because it's on nodal line number 1. Okay? And then they do the same thing and they do a measurement and they say, how long would it go from P1 to P2? So they found P1, P2. What they've noticed is that if they take the difference, we call it the path difference. So basically subtracting the P1S1, subtract the P1S2, they found that it always equals to half of the wavelength, always, okay? So meaning if they repeat this experiment and they say, hey, let's not pick this point as P, I'm going to erase everything here. And they said that if I pick, say this point right here, okay, they can still call this P1. And then if they take a ruler and they connect up the S1, measure how long this is, and they connect it to S2 and they measure how long it is, and if they subtract those two distances, they found that it always equals to half a wavelength. So that's a good pattern to find. Okay, and then they repeatedly did, how about if I put it on point 2? Meaning if I put it on the second nodal line, so now they're talking about this point right here. So they say, if I'm on the second nodal line, any point on there, I can pick this point or I can pick this point, it doesn't matter. But what they notice is that if I connect this to S1 and I say, let's measure how long this line is, and then they say, let's connect it to the second source and I measure how long this is. They found that the difference between these two lines always equals to 1.5 wavelength. And if they repeat the pattern that they're noticing is called the general equation. The difference between the path difference they have. So this would be a good general pattern equation to use if the distance between whatever point to the point source is measurable or the wavelength is measurable. Okay, but then you would run into a situation if the wavelengths are too small or if point P is getting too far away, the path difference between too small that it will be hard to measure it. So the other way to use is you would take advantage of a triangle, okay? And so by comparing the paths difference, you can turn it into a right angle triangle and it would be this. Okay, so you would actually be able to find the relationship by studying the triangle, which we're not going to go into details here. And so this method would not work for light wave. You will find out about that later on when we go into lesson 4, is light wave a particle, or lesson 5 when we go to the Young double slit experiment. So finally they have made a decision that, well, if we can't say measure the wavelength, but if we can measure the distance between the point source, okay, and if I know which nodal line it stands on, and what we can do is we can draw from the right bisector, measure this length from that point to the right bisector, and also know what is the length measuring back to the center point. These are all bigger items that we can measure. They're saying that even if the wavelength is super small, you can still indirectly deduce what it is. Okay, so let's put all the equations together. So basically this is just the extension to the previous equation, which also equals to sine theta n. N is whatever that nodal line that we're on, starting from the middle closest, that n1, and move on, n2, n3, and so on. All right, so let's do examples. The distance from the right bisector to the second nodal line in a 2-point interference pattern is 28 centimeters. The distance from the midpoint between the two sources, point to point P, is 28 centimeters. What is the angle theta 2 for the second nodal line? So what do we know? Okay, so what are these wording? Distance from the right bisector to the second nodal line. Okay, it goes with this picture. Okay, if they say this is N2, okay, the point is on N equals to 2. They have given you the distance from the right bisector. We said that this is called the right bisector, right? The distance from it, this is x2. So they gave you x2 in the question. All right, so that's the first number. So I know that x2 is equals to 8 centimeters. So change that to SI. And then the distance from the midpoint between two source and P is 28 centimeters. So point P to the midpoint. So they gave you L. So the most complicated things is if you have all your equation, you just need to know what are the words that goes with kind of the symbols, right? So they actually give you L is equals to 28 centimeters. So to convert that to SI divided by 100, I have L. They're asking for what is theta 2. Okay, so let's look for it. So we're going to be using, I'm going to highlight the whole equation now. Like this is the equation that we would be using. So basically you have two equations. You have this and you have the path difference. There's two. So if they mention anything like a path difference, you're using this equation. Anything else, you use this. Just figure out which one is your lambda, which one is your d. All right, so let's keep going. I'm looking for what is theta 2. Okay, so I have theta 2, x, and L. So do you see from this equation, I would be using this part of the equation. I'll be using this part of the equation, right? Because I have the x, I have the xn, I have the L, and I have the sine theta. So sine theta n is equals to xn over L, and I'm dealing with the second one. So sine theta 2, sorry, this is a question mark, is equals to x2 over L, which is 0.08 divided by L, 0.08 divided by 0.28, second sine. So it worked out to be 17 degrees. Okay, two identical point sources that are 5 centimeters. The sources are 5 centimeters apart, operating in phase with a frequency of 8 Hertz, generate an interference pattern in a ripple tank. At a certain point on the first nodal line is located 10 centimeters from one source and 11 centimeters from the other source. Calculate the wavelength of the wave and the speed of the wave. They tell you the distance between the 2-point source is 5 centimeters. So I know that is 0.05. It is operating in a frequency of 8 Hertz. From the first nodal line, so we're talking about nodal line number 1, so n equals to 1. The distance, 10 centimeters from one source. This is P1S1 from one of the source is 10 centimeters. And then with the point on 1 to the second source is 11 centimeters, sorry. So it's 0.11 meters. Calculate the wavelength of the wave. Okay, I don't know if you recognize that this is the path difference, so you're going to go to the path difference equation. See, this one doesn't have to divide it by d, so that's like the tricky thing, but you can have your equation sheet in front of you, right? So you don't have to memorize it. Okay, so PNS2 minus PNS1. Does it matter if it's 1 or 2? It doesn't matter. The key thing is the absolute value. I only want the difference. So I take the big one and I minus the smaller one. I think that's the easiest way to do that. So n minus lambda over 2. I'm sorry, I lied. N minus, oh my goodness. N minus half times lambda. Okay, so plugging it in, I'm going to take my 11, so 0.11 minus 0.1 equals to 1 minus half times lambda. So lambda worked out to be 0.020 meters. And then they ask you what are the speed. I want to find the speed. V equals F lambda, the universal wave equation that I mentioned before. So if you don't have that highlighted, you will need to know it. So make sure you know this, right? Universal wave equation, V equals F lambda. That was from grade 11. Okay, so finishing it off. So this is part B. V is F lambda